So we will have like 3 mini sessions. Like in each session, we will have 2 speakers that will talk about their 2 merged papers. Okay, so the first mini session will be on doubly efficient cryptography, commitments, argument, and RAM MPC. This is joined with a reusable online efficient commitment. And the first speaker will be Ethan Mock. And then we will have Dana Shamir to present the other paper. We will keep questions for the end of the talk. So when both speakers are done, feel free to ask questions. I think it's better if you line up to the mic there to be ready to ask your question, and enjoy the session. And please, Ethan, the floor is yours.
Great. Thank you. Thank you for the introduction. This is joint work with Wei-Kai Lin and Daniel Wicks. So the focus of this work is on performing cryptography in a setting where all the parties have like large inputs. And what we want is we want to have to be able to run protocols without having to pay linear time in the input size necessarily. Like especially when a protocol would naturally be thought of as perhaps some sort of like MPC over like RAM functionalities that wouldn't necessarily in the clear need to be pay linear time in its input. We want the crypto version of that to also be sublinear. And so what we have existing in many crypto applications is we have some way of doing cryptographic protocols where the communication complexity is very low, but perhaps the runtime of each party actually has to do a linear scan through their entire inputs. And in fact, this constraint is actually inherent in many contexts. For instance, if you kind of can think of this example of like an MPC for RAM, if there's like any specific location depicted in red here that is like never touched throughout the computation, you can kind of learn that that location wasn't important for the computation, and that gives away some aspect of the security. And so the central question of this work is, can we push all of these sorts of linear time overheads into a single fixed preprocessing phase that occurs where each client individually preprocesses their input, and only then you kind of run an online protocol that can be sublinear time. And so this work is largely inspired by this recent progress on this problem of doubly efficient private information retrieval. This is a problem where there is a server that holds a public database X and a client that holds a location that they want to read from that database. And the server will, and the goal is to retrieve the value of the database at location I without revealing to the server the client's desired location. And so the way this will work is the server does an offline preprocessing that is one-time, deterministic, and fixed. And only then the client can then send query, and the server can respond, and the client can recover the output. And the online phase of this protocol is sublinear. So the recent work by a subset of the current or by the same authors constructs DPIR from the ring LWE assumption, and they get online runtime that is polylogarithmic in the database size, and the preprocessing time is slightly superlinear in the database size. So we kind of want to ask the question of, can we get this exact same idea kind of for different other applications? And so one kind of toy example that we might consider first is the notion of doubly efficient collision-resistant hash functions. And like the question is, can we hash an input in sublinear time in the input size? And you can kind of think of this as being some sort of like interactive commitment protocol. And so what we want it to look like is kind of just a normal hash function, and you sample a seed, and then you get back a hash, and this kind of binds you to the input. But here, we allow that before any of that online stuff happens, the server does a preprocessing phase to get its input. And in terms of security, you want the standard binding notion. And in terms of efficiency, we want that the hash of the hash of X can be computed in sublinear time after seeing S using the preprocessed database. And so you might note that there is a trivial solution to this problem in the CRS model. If the CRS just already includes a hash seed, then the preprocessing can just be compute the hash, and then the online phase is just send over the hash on its own. And so this is kind of like a trivial solution to this problem, but it's kind of unsatisfying, kind of in the sense that, well, like anyone who doesn't trust the CRS, you'd have to like re-preprocess for each group of people that like trusts an individual different CRS. So you can't you can no longer really think of the preprocessing being like one time fixed for all possible parties that you might want to commit to. And so what we want to ask is like, can we do this in the plane model? And it turns out that DPIR actually gives a very natural solution to this, where the way this will work is that DPIR, the server will preprocess the input using DPIR, and then the seed for the hash will be a DPIR query to a random location that is that the client will compute, or that the receiver will compute, and then a hash is just a DPIR response. And kind of the crucial, like, intuitive idea for security here is that any collision must have it be the case, like by DPIR correctness, it must be the case that the collision, the two different values of the collision have the same value at location I. But kind of this violates DPIR security because then the sender then learns that the value that was in the seed is not one of the places that the two different collision value colliding inputs disagree on. And so our result is that we build the DECRHF in this same kind of plane model and with the same sort of efficiency as DPIR, in that there's polylogarithmic online time and slightly superlinear offline time. But there's a kind of an interesting question is like, can we get local opening in this model? And like the kind of standard notion like that we would think is like using a Merkle tree. However, like if you use a Merkle tree, you kind of need to know the hash because you're like iteratively applying the hash many times. So you need to know the hash after knowing the seed, which would require some sort of linear online runtime in order to get locality. And to address this, we introduce a notion of like doubly efficient commitments with local opening. And this is kind of exactly as you might expect with a commitment protocol. It's like an interactive commitment where first the sender on an offline phase preprocesses an input one time, and then there is an interactive commitment phase that the receiver stores a private commitment digest. And then after that, there is an interactive opening phase for a local opening value. And then the receiver can either output the exact bit for the original committed string, or it can reject. And so what we do is we build doubly efficient commitments with this same sort of efficiency properties as DPIR, that we have like a slightly superlinear preprocessing phase and then a polylogarithmic online runtime. There is a caveat to our construction that is like we kind of lack some sort of our construction is not reusable if the sender is able to repeat this process over and over and keep learning the receiver's output bit, whether it accepts or rejects. And to follow in Donna's talk, she will show how their work kind of fixes this problem and gets an improved version. And so I will defer all the technical details for the construction of doubly efficient commitments to her talk. So then kind of building on commitments, we kind of also address the problem of arguments. So here we have a prover and a verifier, where the prover will first preprocess its input into some proof data structure, and then you can run a sublinear time online protocol that allows the verifier to confirm that the statement is true. And kind of the tagline here is again that we preprocess once, and then you can prove the statement to many different verifiers, each in sublinear time. And the construction here is kind of maybe exactly what you'd expect now that we have commitments. Just do Killian. First you generate a PCP for the statement that you're trying to prove, and then you preprocess it using the commitment scheme, and then you commit to the PCP, and the verifier sends PCP queries, and you open to those PCP queries. The verifier can then check both the openings and the PCP verifier and be convinced. So this is so we build a doubly succinct argument. So essentially we has the same rough idea as Killian and same rough efficiency guarantees. And then finally, the last thing that we consider is building MPC for RAM programs. And so this the general notion of doing MPC in a RAM-like way has been considered before, but it's kind of been in this joint preprocessing model. And so the way that this worked is that there is that each of the parties kind of get together in some offline phase and kind of jointly preprocess their inputs, and only then can recover some auxiliary information or preprocessed data structure that was related to their inputs. And afterwards, they can run an MPC protocol that runs in can be in some linear time. And this is kind of unsatisfying for a similar reason we saw before, is that like kind of if you pre-process with one group of people, but then want to evaluate with a different group of people later on, then it's kind of then you kind of have to do a re-preprocessing over again, and the preprocessing is not fixed once and for all. And just a note that RAM MPC would also be interesting in CRS model in some fashion, and this is because RAM MPC already implies deep here, and we don't have any constructions of deep here that are better in the CRS model than what we have in the plain model. And like this, the way the CRS model will work is you have a CRS, and then after that, each party using the CRS can preprocess their input. And only then evaluate a protocol online. And this has the same sort of unsatisfying idea as before, is that if someone doesn't trust the CRS, you kind of have to re-preprocess your input according to that CRS, which is somewhat unsatisfying. And so in our work, we build maliciously secure MPC with preprocessing in the plain model. And it is exactly like all these other constructions where there's a one-time preprocessing, and then perhaps there's a preprocessing of some other party that comes along later, and you can kind of enable these sorts of interactions online there as well. And so just a very super high-level idea of how our construction works, as our goal is to compute a RAM program of many inputs. And we kind of start with this simplified model where we have a trusted RAM processor that is able to evaluate a RAM program in a trusted fashion. And each client will use dpeer to preprocess their input. And then the RAM processor can access each client's input, or each party's input, and run the program. And then we can kind of convert the RAM processor into a circuit by kind of offloading all of the local memory lookups that it would have done to a client holding an ORAM. And then finally, now that we just have a circuit that is doing the trusted processing, we can implement the circuit as a standard MPC. And this gives us a semi-honest RAM MPC. And then finally, in our work, we show that we can upgrade to malicious security by committing to by having each party commit to their input and prove that all of their operations are being done correctly. And this step actually presents one additional technical challenge that I'll just note, is that you kind of need to have to deal with this idea of enforcing consistency between the statement, the inputs that the client committed to, and the statements that they are proving throughout throughout the protocol. And so we solve this technical challenge in our work, and that's how we build fully maliciously secure RAM MPC. So this concludes my section of the talk. I think now I'll hand it off to Donna to give a description of the commitment construction and of the issues with that.
Okay. Hello, everyone. My name is Dana Shamir. Thanks, Ethan, for the previous talk. And I'm going to talk about reusable online efficient commitments, which is a joint work with Nir Bitansky and Omer Panet. Yeah. Okay. So our focus in this work is the notion of online efficient commitments, which Ethan just told you about. They refer to it as doubly efficient commitment, but since the term doubly efficient is a bit overloaded, we prefer the term of online efficient. But this is exactly the same notion. So let me just remind you that in online efficient commitments, we can first pre-process the string in offline time. And then in online time, the sender has access to this pre-processed string, and it should be efficient, usually only logarithmic in the size of the string. And now the sender can commit to the string, and the receiver obtains a digest, and then it can open certain locations that the receiver asks, and the receiver can verify these openings with the digest. And I want to emphasize that we consider repeated openings, which means that the sender commits once, and the receiver might ask to open many different locations. Okay, so this is the notion of online efficient commitments. And let me start with telling you about existing solutions. So Merkle tree solved this, but only in the CRS model. In the plain model, we can use a keyless multi-collision resistant hash, but this is a non-standard assumption. Now, in the plain model with standard assumptions, there is the result that Ethan just told you about, where they construct online efficient commitments assuming ring LW. And the drawback of this construction, comparing to the previous ones, is that it is privately verifiable. It means that the receiver must keep the digest secret, otherwise security is compromised. Now, generally, we try to avoid private memory, and specifically in this setting, it is a problem because the adversary might be able to learn information on the private digest from the bit of whether the opening was accepted or rejected. And since we consider repeated openings, the adversary might be able to learn more and more information from different openings until a point where it has enough information to break binding. This is called the selective rejection attack. And actually, this construction of Mook et al. Is vulnerable to such attacks. Okay, there is a concrete way to get the private digest from the verification. And this is a big disadvantage in the setting of commitments because if the privacy of the digest is compromised, we cannot just generate a new digest. Because if we generate a new one, the adversary might use this opportunity to change the string that it is committing to, and then we lose binding. Okay, so this is a serious problem. And now that we see the existing solution and the problems, let me tell you about our goal and our result. So as I said, there is the construction of Mook et al., where they need a private digest, and also the verification bit must be private. Otherwise, there is a selective rejection attack. And our goal in this, our dream goal is to construct an online efficient commitment with a public digest. Now, in this walk, we make a step towards this dream goal. We construct an online efficient commitment with a private digest, but the verification bit can be public. Okay, so our construction is resilient to selective rejection attacks. And we construct it assuming ring LWE, which is the same assumption that was used in this construction. Okay, so this is our result. And now let me tell you how we do it. So I will start with describing the challenge. We construct a commitment with a private digest. This means that in order to gain security, we need to show that the digest is indeed unknown to the sender. Now, in the result that Ethan told you about, they really show that the interaction hides the digest. But in our case, we want to construct a commitment that is resilient to selective rejection attacks. This means that we need to show that not only the interaction hides the digest, but also the bit of whether the opening was accepted or rejected doesn't add any extra information on it. In other words, we need to show that this bit doesn't leak information. Okay, so this is the challenge, and we observe that we need to solve a leakage problem. So we use tools from leakage resilient crypto. We use an algebraic leakage lemma by Chang et al. That was introduced in the context of memory delegation. And we use it in our context to show that the verification bit doesn't leak any extra information on the private digest. Now, this lemma isn't compatible with the commitment of Mook et al. So our first step is to construct a new commitment that has an algebraic structure. Okay, so our algebraic commitment is inspired by the work of Ishai et al. On linear commitments. And in this commitment, we can use the leakage lemma. And then we can use the leakage lemma to show that the commitment is resilient to selective rejection attacks. So in the rest of the talk, I will tell you about this algebraic commitment and about the leakage lemma, and we'll see how it solves the problem of selective rejection attacks. So what is this algebraic commitment? We start with an algebraic encoding. We use low degree extension to encode the string X that we want to commit to as a multivariate low degree polynomial on some field F. And what is important is that we have a mapping from an index I to an evaluation point, such that evaluating the polynomial on this point gets us the ith bit of the string. And now, once we have this polynomial, we can use its truth table as a database for the doubly efficient peer. So the pre-processing of our commitment will just be the pre-processing of the doubly efficient peer on the truth table. And now in online time, the receiver can privately query the evaluation of every point in the polynomial. So let's see how we use this to construct a commitment. What is our commitment? The sender has access to this pre-processed polynomial. And now to commit, the receiver samples a secret point, z, in the space in f to the m, and it queries it using pil. And the sender responds with the evaluation of the polynomial on this point. And now the receiver keeps the secret point and its value as the digest. So we have the digest, and now to open an index I, the receiver samples a random plane in the space that contains both the point I and the secret point z, and it queries each point in it using pil. So now the response of the sender should be the restriction of the polynomial to this plane. Now, since P is a multivariate low-degree polynomial, the response should be a bivariate low-degree polynomial. So the receiver verifies that this is indeed the case, and it also verifies that the values are consistent with the value in the secret point z and in the index I. So this is the commitment. Now, if the secret point z is indeed unknown to the sender, then binding follows from Schwarz-Zippel lemma, because this adversary cannot, there is a low probability that the adversary can come up with a different polynomial that agrees with the original polynomial in an unknown random point. Now, we use pil in the interaction, so the interaction indeed hides the secret point. But as I said, we need to show that also the bit of whether the opening was accepted or rejected doesn't leak any extra information on the secret point. And this is where the leakage lemma comes in. Now, the leakage lemma is also the reason why we need to use a plane instead of a line, which is enough for Schwarz-Zippel lemma. So what is this leakage lemma? In the leakage lemma, we have a random plane that contains a known point I, and we say that a distinguisher that gets an encryption of this plane, which in our case is done using pil, and a leakage bit on this plane cannot distinguish a random point in the plane from a general random point in the entire space. Okay, so this is the leakage lemma, and this is exactly what we need to show that the verification bit doesn't leak any extra information on the secret points. Now, I'm not going to show you how we use it exactly, but let me just tell you about some additional challenges that we encounter in our analysis. So first, we actually need a super polynomial field in our construction. And this also comes from the leakage lemma. Now, if the field is super polynomial, then the truth table of our polynomial is too big for the doubly efficient field. So actually, we need to introduce a new tool called private polynomial evaluation, which is simply an extension of the doubly efficient pil for large fields. And the second point is that the construction that I just showed you actually only works if the sender acts honestly in the commitment phase. And to deal with malicious committers, we add a proof of knowledge to the commitment phase. And the heart of this proof of knowledge is a new extraction technique of polynomials over large fields, which is inspired by the analysis of Barak and Goldreich in their work on universal arguments. And there are more details in the paper. But that's it. This is the idea of our commitment and of our proof. And let me just conclude with some open questions. So first, there was the dream goal that I mentioned before, which is, can we construct an online efficient commitment with a public digest? And the second question is, it will be interesting to see if you can construct such commitment, assuming just collision-resistant hash, which is the same assumption used in the Merkle tree construction. That's it. Thank you.
Thank you very much. So do we have any question? No question. Okay, I have one question for, maybe it's more for Ethan, like in the, when you were doing like the evaluation of the hash, right? And like, is it difficult like to make sure that the output is not just the output of the hash function, but it's also pseudo-random, kind of making it behave like a random oracle, like a pseudo-random oracle, instead of just turn it on. There is a switch. There is a switch.
I would say I haven't thought about this at all. The DPR responses are like a evaluation points of like smaller polynomials. So I imagine they probably wouldn't look random. So I don't know exactly how to do this first. Yeah.
So I also have a question, sorry. We're going out of time, but like why are you focusing on collision resistance function here? Like why can't you do like better than that?
Again?
Like so why, so you're saying that you want to do an improvement from ring LWE to collision resistant functions, right? Because that's the best you can do. Like you cannot go below collision resistant functions. That's the best assumption you can hope for. Is it true?
Yeah, I think so. I'm not sure, but I guess just because the construction of the Merkle tree that we usually like to use, it uses collision resistant hash. So it's a question to see if we can also make it online efficient.
All right. Okay. Right. So let's thank the speakers again. Like thanks to Dana. Thanks to Ethan. All right. So now we will have another couple of papers that have been merged, and the two papers are linear communication asynchronous complete secret sharing with optimal resiliency. And the other paper is towards achieving asynchronous MPC with linear communication and optimal resiliency.
Hello. Okay.
Fantastic. We will have two speakers. The first speaker will be Cheta Liu Zhang, and the second speaker will be Xiaoyu Ji. And Chenda,
There's a clicker.
what are you missing?
I'm missing
The
the
clicker.
clicker. Like, see this thing? Forward.
Okay, Chenda, the floor
Okay.
is yours.
Yeah. Thanks for the introduction. Yeah, you and I prepared this joint talk where we talk about asynchronous MPC with linear communication and optimal resilience. So let's get started. So we consider the problem of multi-party computation and parties see corruptions. And we consider the setting of guaranteed output delivery where the parties are guaranteed to obtain the correct output by the end of the protocol. So the model that we consider is a little bit different. So in terms of the communication model, we consider asynchronous channels. This means that the messages sent by honest parties are eventually delivered. The adversary acts as the scheduler and can in particular deliver the messages out of order. We consider malicious security, and we don't rely on any crypto assumptions, so we have information theoretic security. So let me start with giving a little bit of motivation for asynchronous protocols, because when you read MPC papers, we mostly consider synchronous. So in a synchronous protocol, we usually have this upper bound delay delta, right? And we rely on that. But the problem is that when we deploy such a protocol over, let's say, something like the internet, the question is, how do we set such a delta, right? If we set delta too small, then because the synchronous protocols rely on this upper bound, then the protocols may lose security or at least liveness. On the other hand, if we set the delta too large, then we may end up with inefficient protocols. So asynchronous protocols are motivated by this problem because they operate well for arbitrary delay network conditions. And as a plus, protocols designed in this model run at the speed of the actual network delay. So what are the differences when we design synchronous or asynchronous protocols. So in a synchronous protocol, because we know about this delay upper bound, if a receiver, for example, is not getting a message after some delta time, then he knows that the sender was corrupted. And therefore, he can assume that some default message, let's say bottom, was received. And because of this, we know that we can achieve MPC with statistical security up to n/2 corruptions, assuming broadcast or correlated randomness. And in the perfect setting, we can tolerate n/3 corruptions. When we move on to the asynchronous settings, parties get messages at different times, right? And if a receiver is waiting for a message, he cannot really distinguish between the case where the sender was honest and his message is being delayed, compared to the case that the sender is actually corrupted and in fact did not send a message. And as a result, we can only achieve statistical MPC up to n/3 corruptions and perfect security up to n/4. So there is this gap between synchronous and asynchronous protocols. So let's get into what we know about the communication complexity of asynchronous MPC, which is the focus of this work. When we think about the perfect setting with optimal resilience n/4, the first work was by Benorcanetti and Goldreich in '93, which gave a protocol with n⁶ communication per multiplication gate. And since then, there have been a long line of works improving this communication. And the recent paper at Eurocrypt achieved the first linear communication protocol for the perfect setting. If we move on to the statistical setting, we know much less. The first work was introduced by Benner, Kelmer, and Rabin in '94, who gave a protocol with n⁻11 communication complexity per multiplication gate. And the state of the art is essentially still n⁴ per multiplication gate. If we compare it to the synchronous setting, we already knew solutions with linear communication since more than a decade ago, due to the works of Ben Sasson-Fair and Ostrowski. And therefore, the question is apparent. Essentially, like if we focus on the statistical security setting with optimal resilience, can we achieve linear communication, right? And this is the question that we are going to answer in this talk. So this is the theorem statement. What is important here is that the answer is yes, we managed to achieve this. Our solution relies on Shamir sharing, so we require a finite field of size n+1. And as a caveat, this should be interpreted as a feasibility result because we have quite large additive terms, right? So as I said, our protocol is based on Shamir sharing. So a sharing is just this degree T polynomial where each party gets 1 point in this polynomial. And the secret is stored at coordinate 0. What is nice about Shamir sharing is that it is linearly homomorphic. Parties can locally add the shares to compute a sharing of the sum of the secrets. We also have error correction. So the general approach is just this seminal BGW approach, right? As usual, parties share their input. We compute jointly a sharing for every internal wire of the circuit. And in the end, the parties reconstruct the sharings for the output wires, right? So we are mainly concerned about the cost of the computation stage. So here we have addition and multiplication gates. Additions are for free because Shamir is homomorphic. Multiplications are processed via Beaver triples as usual. For those that don't know, a Beaver triple is essentially a triplet of values, A, B, and C, where A and B are random, and C is the multiplication of A times B. All these three values are shared with degree T. And what is important here is that to process one multiplication gate, we can use one Beaver triple. And the cost of one multiplication essentially reduces with this equation to 2 public reconstructions. And reconstructing publicly costs n². But thanks to the works of Damkar and Nielsen, we know that we can in fact do a linear number of public reconstructions also at cost n². This means that we can already do process multiplications with linear communication if we have Beaver triples. So the cost of this approach is essentially a linear cost plus whatever it takes to generate the Beaver triples, right? So the focus is, of course, on whether we can generate Beaver triples efficiently. So this consists of 2 steps. First, we need to generate A and B and then C, right? So to generate A and B, we will need to use asynchronous complete secret sharing. This is what Xiaoyu will present in the second part of the talk. And asynchronous complete secret sharing allows a dealer to distribute this degree T Shamir sharing in such a way that the honest parties end up accepting a point in this degree T polynomial. And the best prior work doing this achieved only n cubic communication per sharing. This was CP23. And using super invertible matrices, this would also be the cost for random sharing. And therefore, we are still n square communication away from linear, which is our goal, right? So this is the work that Xiaoyu will present, as I said. The second part of the result is on how to actually generate these triples, assuming that we have an efficient ACSS. So the best prior result essentially achieves quadratic communication, even assuming this efficient ACSS, which is linear. So the part that I will talk about now is, which is this work, is on how to achieve this with linear communication, plus sharing a constant number of degree T sharings, which means that if the ACSS is linear, the overall cost is also linear. Okay, so how does this work? So the prior work, essentially due to CP17, this is Choudhury and Patra, what they did was to generate together 3 polynomials in such a way that each evaluation, so F and G are 2 polynomials of degree, let's say L, and H is the product of F times G. And the idea here is that each evaluation of these 3 polynomials will be shared across the parties. So you can interpret this triplet of sharings as one shared Beaver triple, right? That's kind of the idea. And how does this work? So we will have 2 L+1 parties locally generating triples. So the first L+1 parties will generate a triplet of values, a Beaver triple. For example, P1 generates A1, B1, C1. P2 generates A2, B2, C2, and they will just use ACSS to distribute these locally generated Beaver triples. And because F and G have degree L, then they can essentially use these L+1 values to interpolate the rest of the values of F and G, right? So this is what they do. We cannot do the same for H because H is the multiplication of F times G. So the degree of H is actually 2L, right? We still need more points. So what we do is to use, again, Beaver triples, the Beaver triples that the other parties generated to actually perform this multiplication. So the parties, for example, L+2 up to 2L+1, we will use those Beaver triples to compute the multiplications of the blue rows. So let's look into this approach. So here, because the degree of F is L, then we have essentially L+1 triples, right? But the adversary knows T of the triples here in this approach because T of the triples are generated by corrupted parties. So the maximum amount of triples that we can extract with this approach is something like L+1 minus T. And if you look at the communication complexity of this approach, the cost is L times N. And the number of triples that we obtain is L+1 minus T. Because we need 2 L+1 parties to participate in this process and distribute these Beaver triples that they generated locally, and we are in the asynchronous setting, so we can only count with 2T+1 parties, the maximum amount of triples that we can get is when assigning L equals T. This means that the cost per triple is essentially quadratic. So the question that we did here is whether we can improve these techniques by a linear factor. The answer is yes. And we had these 2 ideas. The first idea is a very simple idea. What if we just increase the parameter L? If the gap between L and T is linear, then we would obtain a linear number of triples, right? And the amortized cost would also be linear, right? The problem here is that even though honest parties participate, the corrupted parties will not participate. So we only have 2T+1 parties helping, but we in fact need 2L+1, right? So this process may get stuck. The second idea that we had is to use packing So if we use this technique, yes, it's true we can only maybe obtain one triple, but if this triple is packed, then, and we pack a linear number of triples, if we somehow can depack this packed triple into n standard Beaver triples, then the amortized cost would still be linear. Problem is that we cannot rely on error correction because these packing techniques require increasing the degree, for example. But in a nutshell, the failure reason is that there may be too many corrupted parties participating in this process. But if you put these two processes together, process one fails because there are too few corrupted parties participating. Process two fails because there are too many corrupted parties participating. So our idea is essentially to nest these two processes together in such a way that the adversary can either participate in both processes or in none of the processes. So we achieve this by saying that a party participates in process two, only listens to a party PI in process two only if this PI distributed his triple in process one. And the effect here is that either there are enough corrupted parties participating in process one, and therefore process one eventually succeeds, or if there are too few parties in process one participating, then there are also too few in process two, and therefore process two succeeds. Okay, so in the rest of the talk, Xiaoyu will talk about how to prepare the A and B.
Hello. Okay. I will introduce the ACSS part. First, I want to give you information about why ACSS is hard to build. Let's consider a corrupt dealer who may send correct shares to honest party P1, but do not send anything to honest party P2. And we assume that after some time tau, honest party P1 will receive his shares from the dealer, but for P2, he will never receive anything. So let's consider when honest party P1 can accept his shares. According to the requirements of ACSS, when an honest party accepts his shares, we require that all honest parties should eventually accept their shares. But so far, P2 has not received anything, so P1 cannot expect it to get any response from P2. This is different from the sequence setting. Maybe in the sequence setting, we can say that if honest party P2 does not receive anything, we can let P2 to make a complaint. But in the asynchronous setting, it's not clear that when honest party P2 can make such a complaint and why party P1 can expect it to receive such a complaint. So maybe in the worst case, when honest parties can accept his shares, he must to make sure that there are at least T+1 honest parties has obtained their shares, and this T+ honest parties can robustly help the rest of honest parties to reconstruct their shares. First, before I talk about the detailed construction of ACSS, I want to first introduce a weaker notion called asynchronous variable secret sharing, or AVSS for short. Different from ACSS, AVSS only requires that when an honest party accepts his shares, all parties can eventually reconstruct the secret. So it's okay to say that for AVSS, we do not require that all parties to get their shares. So the previous work showed how to construct the AVSS protocol with quadratic communication, and then they upgrade to ACSS by only invoking an instance of AVSS. So let's first see how to construct the AVSS protocol. The idea is to use the bivalent polynomial, and it has degree T for both variables. The secret is stored as a position 0, 0, and each party will take a degree T row and the column polynomial as his shares. This can be considered as an extension of the Shamil secret sharing. To make the following construction more simplicity, I will assume a signature scheme here. So in the first step, we will let the dealer send a column polynomial to each party, and each party who receives his column polynomial will compute the signatures on all points of his column polynomial. And then each party sends these signatures back to the dealer, and the dealer will construct a set M such that for each party in this set M, the dealer has received the valid signatures. Here we notice that since there are at least t+1 honest parties in this set M, their column polynomial are sufficient to determine the whole Barrett polynomial. Then in the next step, we'll let the dealer send the row polynomial together with the signatures to each party, and each party will accept his row polynomial only if all these 2t+1 signatures are valid. Here we can claim that if an honest party accepts his row polynomial, then this row polynomial must be correct. That's because among these 2t+1 signatures, at least t+1 of them come from the honest parties, and their shares are sufficient to determine a degree t row polynomial. So all parties will terminate the sharing phase when 2t+1 parties claim that they accept their row polynomial. So for the construction process, all parties in M will send their polynomials together with signatures to all parties, and this time each party can expect it to receive at least the t+1 row polynomial, which are sufficient to interpolate the whole fxy. Everything looks good so far, but we have omitted some issues. For example, actually in the information theoretical setting, the signature scheme is not exist, and the previous work constructs the asynchronous information checking protocol, or ASAP for short, to solve it. But ASAP can only be considered as a weak signature scheme, which is not transferable. The transferable here means that when the dealer sends some message M together with signatures to the first party P1, P1 can convince the next party P2 that, oh, the message originally comes from the dealer. But P2 can no longer do the same thing to convince the next party P3 that the message M originally comes from the dealer. But if we don't care how these issues and how previous work solved them, the communication capacity is already quadratic because the dealer needs to send both the row and the column polynomial to all parties. So a natural solution to say a factor of n is to use higher degree polynomial. Say we can use the degree t 2t Barrett polynomial to store t+1 secrets. And this time, if we do the same thing, we may use a quadratic communication to share t+1 secrets, and the amortized communication becomes linear. But the problem occurs during the reconstruction because each party can only expect it to receive t+1 row polynomial, and the degree of row polynomial is degree t. That is not sufficient to interpolate a degree t 2t fxy. To solve it, let's move back to the first step. Recall that the dealer D has broadcast a set M such that all parties in this set has accepted their degree 2t column polynomial, and the t+1 degree 2t column polynomial are sufficient to determine such a fxy. So can we just use the column polynomial to recover the fxy? Let's have a try. We just let all parties in M to send their column polynomial to the receiver. But the problem here is that the correct party may send, sometimes may send the incorrect column polynomial to the receiver, and the receiver cannot distinguish the incorrect one. So, and sometimes the correct party will also not send the column polynomial to the receiver. So from the view of each receiver, he can expect it to receive t+1 column polynomial. But if we just let each party use the first t+1 column polynomial he received to recover the fxy, that may result in different honest party can recover different results. That is not allowed. So maybe we need to find a way to let all parties can prove that he sent the correct column polynomial to the receiver. The solution is called the authentication tax. The authentication tax is first proposed by BFO12 and is used to build the linear communication asynchronous MPC protocol. And the idea is as follows. For a pair of parties PA and PB, say PA takes a vector of values, message M as input, and we will let PB to choose a random long-term key mu, which has the same length as the message M, and the short-term key mu, which is just one value. Then the authentication tax is defined as the inner product of M and the mu together plus the mu. Once PA can send both the message M and the tag tau to PB, he can convince PB that he sends the correct message M. Here we notice that the long-term key will be used to authenticate different message M, but the short-term key will be refreshed for each time. And the security here comes from that if PA want to cheat, he needs to guess at least one position of mu. So if such a tag can be prepared, then our goal is achieved, and the receiver now can distinguish incorrect column polynomial received from property parties. So for the preparation of these tags, The issue here is we may first let all parties to prepare the authentication keys for each pair of PI and PJ. But the issue here is that proper PJ may not generate the keys mu and the nu. So, but honest party PI still need to generate text for all quarter PJ. So the solution is to let all parties prepare the mu and the nu in a distributed way. At just a high level, we will let all parties invoke another particle ACSS which may has higher communication to prepare a T-share of mu and nu. Since it's a T-share, then later all parties can reconstruct the secrets to PJ. And the reason why we can use the higher communication ACSS particle here as a subparticle to construct our linear ACSS is because the size of the key is sublinear. Then once all parties get the T-share of mu and nu, and if the message M is also T-shared among all parties, then each party can compute a 2T share of tag tau as follows. And they can send the 2T share of tau to the receiver PI. And after receive 2T plus 1 tag tau, maybe PI can reconstruct the tag tau. But the issue here is that how to verify such a 2T sharing. Our observation here is that since this is a sharing phase, we may let the DIR to do something to help PI to do the check. And the idea is that for each party PJ's share of tau, we say tau j, we will let the DIR to help all parties to compute the T share of tau j. Since this is a T share, we can let all parties send this T share to the receiver PI, and the PI can expect it to use the error correction to recover the tau j. And then PI can check whether tau j is equal to what he received from PJ. And it turns out that the authentication tags are more useful. We can directly upgrade our AVSS to ACSS. Recall the reconstruction of AVSS. We reveal all shares to the receiver, but for ACSS, we only want each party to learn his own shares. So can we only reveal the shares that the receiver should know, but nothing else? The answer is yes, and we divide it into two steps. In the first step, we will let all parties to reconstruct the degree T row polynomial, and in the next step, we will let all parties reconstruct the degree 2T column polynomial. Let's have a try. We will let all party PI to who has accepted his column polynomial to send the corresponding shares to each receiver PJ. And recall that at this moment, not all honest parties have get their column polynomial. So PJ can only expect it to receive 2T plus 1 shares and cannot use the error correction to recover his row polynomial. So here we will use the authentication tags, but the tags cannot be directly applied here because this is just one value, not a column polynomial. To solve it, our observation is that when the long-term key is the same, the authentication tags are linear homomorphic. So we can let all parties to send a batch of values to the receiver PJ. And PJ will ask all parties in M to reconstruct a random linear combination of the bivalent polynomial. This reconstruction process can be considered as a reconstruction process of AVSS. So this can be finished with the help of the tags. So as a result, each party PJ can expect it to receive T plus 1 correct shares, which is sufficient to determine his row polynomial. The reconstruction of column polynomial is similar, and I will skip this part. To summarize, in our work, we first build the AVSS protocol with the linear communication, then upgrade it to ACSS by only invoking one instance of AVSS. That's all. Thank you.
Okay, maybe while the next speaker sets up, do we have questions for any of the speaker? Yeah. So if there are no questions in the interest of time, I would say to thank the speakers again and start back. Okay, so the next mini session is about like two papers. The first one is cheater identification on a budget, MPC with identifiable abort from pairwise maps. And the other paper is secure multi-party computation with identifiable abort from vindicating release. The first speaker will be Nicola Melissaris, and then we will have Jack Dorner. And Nicolas, the floor is yours.
Hello. We're cool. hear me? All right. This is how it's supposed to go. All right. Hi, I'm going to give the first talk of this soft merge, cheater identification on a budget, MPC with identifiable abort from Pairwise Max, joint work with Karsten Baum from DTU, Rahul Ratri from Visa Research, and Peter Scholl from Oxford University. So since this is the MPC track, I'm going to skip the very regular intro that you usually get. I'm going to jump straight into identifiable abort. When we have a protocol in the presence of some adversary, we want it to have some properties, and we want it to be correct. We want it to protect our input, and we want to have guaranteed output delivery or fairness. Now, unfortunately, from some results from a long time ago, in the presence of dishonest majority, we cannot have guaranteed output delivery or fairness. Now, what can we do about it? We didn't give up. And what's the next thing? When I say we, I mean cryptographers, right? Not we, the authors. What we can do is we can put forward a new property, which is called identifiable abort. What is identifiable abort? It's a property according to which whether everyone gets the output, or in the case of an abort, honest parties learn the identity of at least one of the cheaters. Now, why do we care about it? If we have a dishonest majority protocol, the adversary can have a trivial denial of service attacks. Imagine a auction where people place their bids, adversary eventually gets whatever information they're supposed to get, they abort the protocol, they know the highest bid, no repercussions, nothing is going on. So having identifiable abort, what we can do is we can learn their identity, kick them out of the protocol, then rerun it with the remaining parties, and eventually we can have what we want. Okay, so although you can tweak the GMW compiler to get identifiable abort, the first paper that really took a shot at it systematically was this paper from Ishai Ostrovsky and Zikas from Crypto 2014. And when considering solely a preprocessing protocol, the IOZ, I'm going to call this IOZ, okay, IOZ compiler, it's pretty simple and intuitive. So the idea is first to commit to all of the random tapes, then run a standard secure with abort protocol. And if the protocol aborts, then everybody opens their commitments to the random tapes, then everyone can locally rerun the computation, find out who cheated, everything is good. Now, because this is pre-processing, it doesn't matter if the random tapes are open, because in the pre-processing doesn't depend on the private inputs, the parties' inputs. Okay, so in order for this idea to work, we want to be able to detect deviation from the honest protocol using the randomness that the party is committed to. Now, the challenge in all of this is simulating the view of the corrupt parties. If the protocol aborts, the simulator needs to be able to open the honest party's random tapes to the adversary in a way that it explains what the adversary has seen already, like the simulated transcript. Now, one way to do this is if the preprocessing protocol is adaptively secure, honest random tapes can be explained by the simulator as if the party had been adaptively corrupted by the adversary. By the adversary. Now, this is the reliance that the IOZ compiler has on adaptive OT, and it kind of seems inherent to this commit and open paradigm. So IOZ, first construction that makes black box use of cryptographic primitives, but it requires adaptively secure OT. I don't like that. And every step, every round, you need to prove in zero knowledge that everything is done correctly. There is some related work. Baum, Orsini, Scholl, Spini, Fair, Cunningham, Fuller, Yakubov avoid generic zero knowledge, but they still have expensive preprocessing. Baum, Orsini, Scholl, Soria, Vasquez avoid zero knowledge and adaptive OT, but it's only for Boolean garbled circuits. Now, To allow identifiable abort in the online phase, remember how I only talked about the pre-processing phase, our main tool is our new compiler that transforms sender classes of sender-receiver protocols, which is when just the sender has input, the other people do not, into one that supports cheater identification. Our compiler overcomes the limitations that the IOZ compiler had, which was only for pre-processing protocols, and it doesn't need to rely on adaptive primitives like the previous one. A key feature for a protocol is it has a very simple online phase, is based on pairwise informatic theoretic max, like in the secure with abort Bedoza protocol. Thanks to this simple online phase, the correlated randomness that we need to produce is just simple authenticated triples, the same as any secure with abort protocol. Okay, so as I said, we present this compiler, works for a general class of sender-receiver protocols. Only one party has input, exactly like IOZ. We make black box use of the underlying secure with abort protocol. Unlike IOZ, we are not restricted to pre-processing protocols. So this allows us to apply our compiler to an arbitrary linearly homomorphic commitment scheme, multiple receivers, which we can instantiate with like a vol-based protocol for setting up information theoretic max. At a high level, it follows the same strategy as our pre-processing phase, except that to prevent leakage of the center's private inputs, we only require the receivers to commit and open the commitments to the random tapes. Now, there is a mild assumption on the communication pattern, which we can talk about. This is the receivers do not talk to each other. We can show that the receivers will still be able to identify a cheating sender, since in this case, there will always be an honest receiver that follows the protocol and abort it due to the cheating sender. Now, there is an issue with this approach. Even though receivers do not have private inputs, they might have private outputs. So we don't want to reveal that. To remedy this, we have two different types of recovery mechanisms, depending on who aborted. Okay, in the first case, all right. So in the first case, receivers all privately send their evidence to the sender, selects who cheated, publishes a proof. In the second case, the receiver must immediately open using broadcast, okay? Open its view for all parties to inspect and confirm that it aborted. And because of the restricted communication that I mentioned before, that would imply that the sender has cheated. So it's not a problem to reveal the receiver's output because it would depend on the corrupt sender's input. Now, the final challenge in our compiler is ensuring that in all of identification stages where the honest receivers open the random tapes, they can be simulated. Now, instead of relying on adaptive security, which would be the obvious thing to do, we observe that a weaker property suffices, which we call online extractability. Now, in the UC security proof, when an adversary corrupts the sender and possibly a subset of receivers, the main job of the simulator is to simulate messages from honest receivers in a way that they can extract the inputs of the corrupted sender. If the simulator later has to open the honest receiver's random tapes, due to malicious sender causing an abort, the natural approach would be to rely on adaptive security. So, what is online extractability? It's a special type of simulation when the normal protocol execution is enough to extract adversarial inputs if you do imperceptible changes to a CRS. Now, this is how many UC protocol simulators work, but we define this property formally. We show that it composes. Now, having online extractability, the task of the simulator for identifiable abort becomes easy. It can just simulate the messages of the honest receivers by simply running an honest execution of the protocol without interacting with the CRS. Now, this makes it pretty trivial to open the random tape and identify a cheater, since the simulator has followed the protocol honestly. All right, so we have like our homomorphic commitment that I talked about before. How do we build an MPC protocol? Commit to random shares, commit to tapes for triple generation. Here is where we can avoid adaptive security, because when we commit to the randomness for triple generation, we don't need to run the triple simulator. We can just extract the values from HCOM from before. Okay, generate triples, commit inputs, run triple sacrifice. If everything goes fine, run the simple online phase. If fail, identify cheaters, do the thing I mentioned in the beginning. Now, to see how well this performs, we compare the protocol to two versions of pre-processing and online phases from Le Mans, from Rahul, Ratchery and Shaw, 2022, here, crypto, which is secure with a board. Now, the first one has less processing, does worse online. V2 has more pre-processing, does better online. Now, both of these and our work require n-squared OLE correlations for each multiplication gate. We also have, if we use like our state-of-the-art PCG techniques, producing these OLEs will take n-squared times circuit size. Now, our pre-processing phase is the same as the Le Mans, but it has an additional factor, which is to authenticate and check the triples. When it comes to the online phase, we use standard Bedoza, and it has authenticated triples, signatures added to messages, and it will increase the cost by like an O of n. All right, I'm going to be a little bit faster with this. And the adversary, this is like the word case, the adversary can always increase the cost of pre-processing by forcing procedures to be, complaint procedures to be run, right? They could always send invalid messages, and they can force everything through a broadcast channel. This would increase the complexity by a factor of 2 because you have to use the broadcast instead of point-to-point channels. Now, the adversary could also cause an abort at any point, forcing parties to open their views. But in our protocol, it's fairly cheap to resolve aborts, because once the parties receive the views, they only need to locally compute the messages with no need of expensive ZK proofs. And I'm going to hand over to Jack.
Right. Hi, everyone. I'm Jack. This is joint work with Ron and Yash and Abi. We're going to start with the title. So hopefully everybody already knows what MPC with identifiable abort is. I'm not going to explain that, which just leaves vindicating release. And unfortunately, I don't have very much time, so I'm not going to be able to say anything formal about it or even give you a good example. I'll just give you a bit of high-level intuition to start with. This is a descriptor that we came up with for the naive approach. The first thing that you want to do when you first hear about identifiable abort, which is if somebody cheats and the protocol aborts, the obvious thing to do is just have everybody somehow open their random state to prove that they did your computations correctly. And this is a really simple idea to come up with, but it does run into some problems pretty quickly when you try to do it. First of all, it typically requires you to have adaptive security for whatever protocol you're using. And second of all, it requires you probably to release everybody's inputs, which is a problem if they are secret. So the history of identifiable abort techniques is kind of the history of trying to avoid this. GMW back in 1987 proposed to use zero knowledge to prove that computations were performed correctly. But of course, this requires you to use your underlying protocol in a non-black box fashion. And then there was a big gap, and Ashai et al. Suggested to use information theoretic zero knowledge techniques with a pre-processing model. And then if the pre-processing protocol fails, you can open the random tapes for that. This does require an adaptively secure OT protocol. A few years later, we had Balmersini and Scholl that suggested, again, to use zero knowledge, but just specifically over somewhat homomorphic encryption, not over an arbitrary protocol. And finally, the same group, but with Cirio Vasquez, returned to the sort of computational online phase that, say, GMW had, and gave a method to do it with additive homomorphic commitments, excuse me. This only works for Boolean circuits, however. And in spite of this variety of techniques, there's actually one thing that 3 of these 4 papers share, along with the one that was just presented, which is that they all construct at least one protocol compiler. So the way that these techniques work is you start with some protocol, you put it into a transformation that mangles it somehow, and what you get at the end has identifiable abort. And this is a good technique. It seems to work really well. The problem is it's a bit complex, right? It's kind of hard to understand, it's difficult to describe, and it's especially difficult to implement. So as far as I know, none of these were ever implemented, and I'm not quite sure about what came before. Perhaps I think that one has been. But by comparison, if we look at the non-identifiable abort world, we do have protocols that are kind of like the ones at the left that use exotic primitives and maybe are kind of compiler-oriented and get a lot of efficiency, maybe concrete, maybe asymptotic out of this. But we also have another pathway. So we have a sort of simple, well-recognized fundamental primitive for multi-party computation, which is oblivious transfer. And we've known that it's complete for MPC for almost 40 years at this point. And we know how to construct protocols that are information theoretically secure in only the OT hybrid model. So just using the OT functionality, nothing about a protocol here. And these protocols tend to be really easy to understand, really easy to implement. And in spite of that, they're actually efficient enough to be deployed in the real world in some scenario. Not only that, but they're typically relatively modular. So they benefit from improvements elsewhere in the literature. And when we make improvements here, those improvements also tend to apply to purpose-specific protocols that achieve specific tasks. So maybe the definitive example of something like this is the mascot protocol from Keller, Orsini, and Scholl. But of course, there's lots of others as well. And the goal of this work is to make the identifiable abort world more like the non-identifiable abort world. So we'd like to propose some kind of simple fundamental primitive, something that hopefully is a little bit like OT. Then we'd like to construct generic MPC in just the hybrid model of that fundamental primitive. We'd like it to be information theoretically secure. And we would like the techniques that we use, both the protocols and the proofs of security, to be very similar to what we know, what we're super familiar with from the non-identifiable abort world. So preferably like to modify existing protocols in really minimal ways. And in service of these goals, I'm going to forbid myself some words for the rest of this talk. So we're not going to use the words non-black box or adaptive or homomorphic or compiler. And I'm going to add one to the list from earlier, which is straight line extraction. So we're going to forbid ourselves the Fischl transform and Conditionlat and UNRWA and anything like that. So are we clicking? There we go. All right, so let's start with the fundamental primitive. We'd like to use OT. Unfortunately, we can't, and this is because thanks to Beaver, we know that there's a 2-party correlation that implies OT information theoretically. And then a bit later, thanks to Ashai et al., we know that identifiable abort is separated from all 2-party correlations. So we can't possibly get identifiable abort in general out of just OT, but maybe we can modify it in some kind of minimal way. So what's the minimal modification we can make to the OT functionality so that we can get identifiable abort out of it? And I claim that the first thing is that OT is a 2-party functionality. So you have a sender and you have a receiver. I'm going to call them Alice and Bob. But in general, we want to work with n parties. And it had better be the case that the n-2 parties that aren't involved in an instance of OT, if the instance aborts, those other parties need to find out that it aborted and who caused it to abort. Otherwise, how could they possibly attribute it? So the first thing we're going to do is add identifiable abort for n parties to just the 2-party OT functionality. And this makes it kind of properly an n-party thing, right? This gets us around the 2-party correlation separation. But unfortunately, this isn't quite enough because we're going to be building a protocol in the hybrid model of this. And what happens if the protocol we build aborts? Well, somehow we're going to have to figure out who cheated. And here there's nothing binding anybody to their input. So it's possible that somebody could cheat just by putting the wrong thing into an OT instance and then later lying about it. And right here, we have no way to tell who lied about putting the wrong input into their OT instance. So we need to make another change. And I don't want to do any math inside the OT. I don't want to commit to like a particular macking scheme or anything like that. So we'll do something really simple. We're going to give Alice another instruction that she can call later reactively after we're done doing the basic OT thing. And this will simply forward her inputs to everybody else who's involved in the protocol reliably. And notice that this binds Alice to her inputs. It doesn't explicitly bind Bob, but Bob implicitly is bound as well. Just through the natural mechanism of OT, because if Alice puts something unpredictable into her side, Bob can't possibly guess the message that he didn't select. Therefore, M sub B on the screen here actually binds Bob to his input bit as well. Before I move on, just a couple of simple observations. So first of all, this functionality is reactive. So opening is a voluntary action that people have to sort of actively take. And it's asymmetric. So only Alice opens her inputs when the open instruction is called. This means that Bob's input, if it must be, can be kept secret, and this is going to allow us to recover input privacy somewhere higher up the stack of protocol constructions. And finally, I want to observe that the n-2 parties who are neither the sender nor the receiver are completely passive. They only listen to the functionality. They never send anything. And this property holds for protocols that realize the functionality as well. So the observers will only ever listen to a broadcast channel. They will never, ever transmit anything. In the paper, we give 3 different ways to realize this functionality. So first of all, we show that it can be realized information theoretically using a simple depth 1 correlation. This is just the basic OT correlation plus some max for the observing parties. Second of all, we give a direct computational realization that's derived from PBW running over a broadcast channel. We just add a simple kind of Schnorr type sigma protocol for the open instruction. And this means that it's instantiable from the exact same assumptions as PBW. It can be DDH, it can be LWE, it can be DCR plus QR. And actually, it's also composable without relying on a straight line extraction transform. I forbid myself the word, and I just used it, I know, but we don't use the technique. So finally, we show that you can also do OT extension for this thing we call Scott, sender committed OT. And we can do it using a very simple modification of existing OT extension protocols. We use soft-spoken OT. We add just a little bit of vindicating release, meaning we open some intermediate protocol state using the basic functionality. This is a super minimal change. There's maybe just an extra paragraph in the proof and a couple of extra instructions. And the number of public key operations is it should be in any OT extension protocol independent of the batch size. Unfortunately, for this last one, we do require a programmable random oracle. This is the only place in the paper we need it. And this protocol is just about concrete efficiency. So we think that that is a reasonable trade. So once you have sender committed oblivious transfer, we build kind of a stack of protocols on top of that. I'm not going to go into details on any of them, but I'm going to give you kind of a roadmap. So the first thing that we propose is an analogous modification of vector OLE, a committed vol where the 2 participants, one of whom has a scalar and one of whom has a vector, can decommit their inputs. Either one of them can or both of them can at a later point. And we show how that you can realize this functionality information theoretically in the Scott hybrid model. This is based on a very simple modification of the OT to OLE transformation from the sequence of threshold ECDSA papers. Really, it's just an extra instruction and an extra line or 2 in the proof. From there, we can use the mascot protocol, again, just with a little bit of indicating release, adding a step to release a little bit of intermediate protocol state using that open instruction. We construct a preprocessing functionality with this. Again, it's information theoretically secure, a very minimal change. And once you have a preprocessing functionality, you can preprocess for pretty much any of the online phases from the literature that you like. We don't propose a new one. So you can use IOZ, you can use BOS 16, but really we suggest that you use the online phase from the paper that was just presented because it's much more asymptotically and concretely secure, efficient than prior works. Okay, so here we have the stack. We achieve MPC with true IA. We even get input privacy at the end. Everything here is information theoretic. Everything here is a well-known existing protocol with just a handful of minor changes to the proof and to the protocol itself. There's a couple more things I wanted. I wanted to show you that it was modular and reusable. And also, we would like to show that there's some manner of concrete efficiency here. We said that the non-IA world was reasonably concrete efficient. And in service of that, we also show that you can construct threshold ECDSA just by modifying this threshold ECDSA protocol that was presented at SMP. Again, we add some intermediate protocol state release and a little bit of lightweight zero knowledge that we need for a technical reason. And the result is something with 7 rounds. It's about 3 times the cost without identifiable abort. And that means that it's actually faster than many deployed threshold ECDSA protocols that don't have identifiable abort. And I hope that this is some kind of evidence that these techniques, at least in some contexts, are reasonably practical. All right, so I'm almost done. Before I close, there's one more thing I want to talk about, which is
try to wrap up.
we're going to get cut off.
Yes.
Okay, all right, then I'm done. Oop.
All right. Thank you very much. Maybe we have time for a very quick question. Questions. Okay, let's thank all the speakers again and enjoy.